solve the problem. Another concept for the network is the residual graph. Residual is mean that the remaining amount, okay? And residual graph, for the edge that can admit more flow. It means that the arc have some remaining capacity. We can send more flow on that. Okay. For example, if the channel graph is G and G with the set of vertices and the edge E, then we call that residual noted at V and E prime. Okay. And therefore, for each arc U and V, we call that the residual flow. It means that the remaining flow will be the capacity of the arc minus for the current flow. If residual values bigger than zero, then the arc UV belong to E prime, the set of E prime. For example, look on this graph. You see that here for this graph, we have one arc, two arcs, three arcs, four arcs, and three arcs. Okay. In this case, for the arc S and T, this one we call this arc a residual because we have remaining flow will be capacity is 5 minus for the current flow is 2. Therefore, the remaining flow will be 3. In this also, residual flow of arc B to A is 4. Here, B to A is 4. The residual arc for S to B will be 1. Okay, S to B will be 1. Okay, but in this one, we don't have residual flow from A to T because it's 0. We don't have the flow arc. From B to T also the same because we don't have residual values. Okay, because 5 minus 5 is 0. Therefore, we don't have flow. And in the reverse way, okay, you see that in the reverse way, when we flow here, it means that in the reverse way, we have the remaining flow fly back, and in the reverse directions, the residual value will be 2 because we can send here 2, therefore we can send back 2. Okay. Similarly, in this one, we flow here 7, flow here 7, therefore we can flow back is 7. And similarly, 4 here go forward is 4, therefore the residual one to flow back is 4. And the reverse one is 5 also. Then this is residual graph for this graph. Okay. Then when we define residual graph from a certain graph, the first step we need to identify the remaining flow for the original direction for each arc. Then after that, we take the reverse direction for the reverse flow also. Okay. That is a kind of network. Now, that's a very simple concept for you to know how to present a distribution network. Okay, now it's the time to formulate the problem in linear programming models. In this case, we should start the capacity of the arc. Will be understand that we can transport the maximum amount of flows from the starting point and terminal point of the arc. Okay, that's the maximum amount we can carry on this arc. Okay, that's the capacity of the arc. Therefore, if we let the volume of flow pass through the arc ing will be xig, and x0 is very special flow. That is the total flow enter the sync node. Okay, that's the enter the final flow. Okay, the sync node is the final node. The most important condition for the flow to be feasible is the volume if flow on the arc should be bigger than or equal to 0, but not more than its capacities of the arc. And the total flow into the node I should be equal to the flow out of node I. Based on that, we can formulate the maximum flow problem as follows. You see that here, that's the total flow. In the slide I sent to you, I put SO and ST, but please here to coincide with the graph, just remove the O and remove S here. We have the source node and the sink node here, and the total flow to go out from the source node. Suppose that I draw the virtual node, virtual arc here, then I have the total x0 will be the total flow in node. Okay, then total flow in node S will equal to the total flow out node S, sum of flow from S to node I. Okay, node I here in this case 1 and 3. Okay, xi and S1 and S3, and the flow of S2 is 0, S4 is 0, and ST is 0. Okay, therefore we have the first constraint here. And the second constraint is the constraint for the middle flow, middle node. That is all of node in the middle, from node K, from 1 to 2 to N. We will see that the total flow from node K, total flow in, that is xik to flow node I in node K, will equal to the flow out of node K, that is xkj. Okay. You flow out. Okay, that is the condition of total flow in and flow out. Actually, at the source node or the sink node, we still follow this rule, but that is represented by the artificial arc here. Okay, in the last node, the sink node also, we have the artificial arc here, in which the total flow out, that is x0, will equal to the total sum of flow in. Okay, you see, total flow of flow in. And we have very important constraint that all of flow on the arc will be bigger than or equal to 0 and smaller than capacity. Okay, right? And you see that. And our duty is try to maximize the flow x0. Okay, that's it. That is the formulation of the maximum flow problem. And our objective is try to find out the flow for each arc and maximize the total flow for the sink and the source and the signal. Now look on the example, numerical example for you to understand better. For example, this is oil companies like PV oils or like Petrolimex. Okay, suppose that they want to shift the maximum flow of the oil per hour via their pipeline or via their vehicle to carry the tank of oil from source node to the sink node through different station here. Okay, here on its way from nodes SO and SI oil must pass through some own station 1, 2, 3, 1, 2, 3. Okay, the maximum number of barrels of oil, million of barrels per hour, let's say that, can be pumped through each arc is shown in the table. It means that the capacity, maximum flow, is means that the capacity for each arc. For example, SO to 1, the capacity is 2. The SO to 2, the capacity is 3. 1 to 2 is 3. The capacity of 1 to 3 is 4. 3 to S to sink node is 1. And 2 to sink node is 2. And this one is the artificial arc. Therefore, we just show that it's 0. Okay, that's the one we want to maximize. Okay, now to formulate this problem like linear programming, we can formulate like this. That's a maximize is 0. First of all, this is the constraints for the capacity. All of flow for each network, each arc will be less than the capacity. That's the first condition. That's the arc here. The first arc is SO to 1. SO to 1. The second arc is 1 to 2. SO to 2, sorry. SO to 2. What else? What's wrong?
Yeah.
Okay. Let me show the here, because I have to use that one because some of you come late. I have to come back here. Okay, you see that here. The first constraint will be the capacity constraints. It means that the flow on all of R should be less than its capacity. The arc SO to 1 should be less than SO to 1, less than its capacity 2. The SO to 2 should be less than its capacity 3. SO to 2 is less than 3. As the flow is 1, 2, less than 3. Is 1, 2, less than 3. 1, 2, less than 3. Capacity here. 1, 4, less than 4. 1, 4, less than 1, 3, less than 4. And 2 sync, 2 ST. 2 ST less than 2. 2 SI, sorry, sync. 2 SI less than 2. 3 SI less than 1. Okay. 3 SI less than 1. Okay, something like this. And the condition for the flow should be non-negative. And in the middle one is the flow constraint. We call that flow constraint. It means that the total flow out in each node will be equal to the flow in, total flow in. In this case, you see that flow out, flow in of SO, that's the artificial flow, that's H0, will be equal to total flow out, that's SO1 plus SO2. You will see here. H0 equal to SO1 plus SO2. So the flow of node 1 and node 1, the total flow in will be XSO1 equal to the total flow out, that X12 and X13. Yeah. XSO1 equal to X12 plus X13. And node 2. Node 2, you see that we have two flow in, that is X12 and SO2 will equal to the total flow out is X2 sync. Okay, here. XSO2 plus X12 equal to X2 ST sync. Okay, SI. Then node 3. Node 3 will be one flow in, that is 1, 3 equal to flow X1, X3 SI. Okay, X3 SI. Yeah, and then it's finished. You see that it's very simple. Actually, this model you can solve by simplex easily because it's very small. And this is a variable here, a real number. Therefore, it can solve very fast. But in real life, especially in distribution system, the quantity here is not the real number. It will be integer. Therefore, normally it's very hard to solve. It takes long time. And secondly, we have the big size. It means that we have many nodes. We have many arcs. Therefore, the size of problem is very big. If you use a simplex, it may take few hours to solve it. It's not good. Therefore, we need some other algorithms to solve that. The first algorithm to solve it is developed by Fox and Fulkerson for a long time ago, around 78. The idea of Fox and Fulkerson at that time, they developed to answer two main questions. If we have the feasible flow, it means that the flow satisfies the capacity constraints, satisfies the flow balance constraints, then how can we tell if it's optimal flow or not? Okay, it means that maximize is 0. The second question, that if there is a feasible flow, it's non-optimal. Therefore, is there any way we can modify that flow in order to increase or to increase the flow from the source and to the sink node in order to maximize this? Based on that, they start to observe some characteristic of this flow in order to develop the method. The first properties, they say that If the flow through the arc ing is below the capacity, therefore it means that in this arc we can increase the flow, right? If the current flow in the arc less than the capacity, therefore we have the chance to increase the arc up, right? Therefore, we call this arc is the uh, uh, increase set of arc. Okay, we will in the network we will identify all of arc can be increased or not. Okay, we call this set is increase set. The second property is if the flow in the arc is positive, therefore we can modify that flow by reduce that. Okay, if it's not bigger than zero, then we can reduce that. In that case, the flow through the arc we call that reduce arc, and all of these arc we set it in the set of reduced arc. Okay. Therefore, basically in the network we have two kind of arc. The first one is increased arc. If is flow less than the capacity. The other one is the reduced arc. If the current flow in the arc bigger than zero, therefore we can reduce. Okay, that's now look on this. Look on the example. You will see what kind of arc to be increased or decreased or reduced. Okay, for example, in these networks, the capacity is the outside number, and the current flow is inside number. Okay, therefore in this case, you see that with this arc, the current flow is 1 less than capacity. Therefore, this arc will be increased arc. Besides that, the flow here is positive. Therefore, it can reduce. Therefore, it's also is reduced arc. For this arc, you see that the capacity is 1. The current flow is 0. Therefore, this arc can increase only. Because the current flow is 0, we cannot reduce anymore. Therefore, it cannot be reduced arc. For this arc also, capacity is 3, current flow is 0. Therefore, we can increase the flow, but we cannot reduce because the values of the current flow is 0. Therefore, this arc is increased arc. For this arc, the current flow is 1, the capacity is 1. Therefore, we cannot increase anymore. It's equal to the capacity already. Therefore, but the value of current flow is positive. Therefore, we can reduce. Therefore, this arc we call that reduced arc, and so on. Okay, that's the way. Now, based on this characteristic, we have the way to find out the maximum flow by force and Fulkerson labeling procedure. The purpose of this algorithm is to modify the feasible flow in an effort to increase the flow from the source to the sink. Okay, we change the value of the flow from each arc in order to make it bigger. The first step, we label the source. It means that we mark that, okay, the source is checked it already. The label here is mean that marking. Step number 2, we label node and arc except the arc X0 or A0. The arc X0 is A0 is artificial arc, come back from the sink to the source node like this. That's it. That is A0 arc. Okay. We label the node and arc except the artificial arc. Sorry, let me stop a little bit. Okay. Then you see that we will consider to label the node and arc except the artificial arc of A0 to come back to represent the flow, total flow. we follow the rule is like this. If the node X is labeled, if the node is already labeled, then node Y of the arc X and Y is unlabeled. And this arc is a member of increased arc. Then we will label node Y. And the arc X and Y. In this case, the arc will be X and Y is the forward arc. Okay. Remember that in the condition for forward arc is the original node is labeled already. The destination node is not labeled yet. And this arc is the increased arc that we call that this forward arc. In the backward arc is reverse way. It means that the backward arc is mean that it go from Y to X. If the Y is unlabeled, but the X already labeled, and X will be the member of reduced arc. Therefore, this arc we call that backward arc. Okay. Therefore, the step 2 we will check what is the forward arc, what is the backward arc totally. Then we continue this label process until the sink has been labeled or until no more node can be labeled. If the sink cannot be labeled, the current flow is optimal. That's it. But you see that it's not finished yet, because in the middle normally we cannot label all of the nodes. Therefore, we will find out the chain of label arc called C, leading from the sink to source, to adjust flow of the arc C, that we can maintain the physical flow to increase the total flow from the sink by 2 cases. The first case, the chain of the arc C consists only forward arc, therefore it is optimum. But the second case, if C contains both backward and forward arc, we try to increase the flow. That's the way we change the flow from the current flow. Okay, to increase the flow from source to the sink and decrease the flow in all C backward arcs by the mean of K1 and K2. K1 is the mean of reduced arc, and K2 is the mean of increased arc. Okay, then we will adjust all of arc by these values, by the smallest value. Okay, now look on the example, you will understand better. Suppose that we have the network like this. Okay, this is the artificial arc, and this one you see that's a source node and the sink node, and this the capacity is fine, the current flow is 2, the current flow is 2, and so on. And this case you see that all of this one will be, you see that this label, this unlabeled, therefore we label this, therefore the chain in this one will be 2, and therefore the flow from source to sink is 2. Okay, that's the total flow is 2. Yeah. Then if we have the way, suppose that we increase 1 unit here, therefore automatically we increase 1 unit here, 1 unit here, therefore the total flow from the source to the sink is 3. You see, that's it. Now, that is the case number 1. Case number 1 is the minimum flow we can increase until we cannot increase anymore. For example, in this case, we can increase maximum 3 because the capacity of this one is 3. All are forward arc. That's the mean of the increased values. Okay, that's it. We can increase up to 3 only, no more. That's the flow from the sink. But for the case of number 2, in which the network we have both reduced arc and increased arc. Therefore, in that case, the first step we need to find out K1. Okay, K1 in the minimum of reduced values, and K2 in the minimum of increased values. Okay, here look at this. Suppose that consider in this arc, and the initial flow is like that. This is the capacity, this the outside number capacity, and the inside the current flow. Okay, and you will see for the reduced arc, you see that the maximum, the minimum reduced This arc reduce is 2, right? This arc reduce value will be 2. This arc reduce value will be 0. Therefore, its mean is 0, right? Sorry, this is increase. This arc is reduce is 2. This arc reduce is 2, right? Therefore, the minimum reduce value K1 will be how much? Will be 2, correct? Okay. But for the increased arc, the increased value for this one is 4. Increased value for this one is 1. Increase for this one is 1. Increase for this one is 3. Therefore, what is the minimum K2? K2 minimum K2 is how much? Okay, let me write down first. Write down for you. K1 is 2, right? Because here 2 reduce to 2, 2 reduce 2, therefore minimum of all of this is 2. How about K2? K2 is mean of what? Mean of K2 is mean of reduce, right? Reduce for the mean of increase, sorry, mean of increase. K2 is mean of increase. Increase of 2 and 1 and 3 is 4, right? Because mass capacity 4, the current flow is 4, 0, sorry. It's 4, right? And how about this one? The increase of this one is 1, right? The increase of this arc is 0 to 1 is 1, right? Therefore, K2 is 1. And the third step is we need to find out the K. K is the mean of K1 and K2, right? Mean of K1 is 2 and K2 is 1. Therefore, it's equal to 1. Therefore, after find out K1 and K, we can adjust the degree flow to increase 1 unit and equal to increase 1. Therefore, here you see that this one is reduced flow, correct? Here, we increase flow. Sorry, we increase only because that belongs to K1, K2. Therefore, reduce we cannot reduce. We don't reduce. But in this one, we increase 1, correct? 1 here, and increase here we increase 1. And in this one, we reduce 1 and increase 1, and therefore you see that, first of all, hold on. In that case, we will not know that, okay, decrease or increase, because in this one, you see that it's increase. It can increase 1, but also reduce 2, right? Increase 1 and reduce 2. Therefore, how much? That is 1. You see that? Increase, reduce 2 is 0, increase 1 is 1. Therefore, it is 1. And you see that it's increase 1. It's increase 1, right? And you see that after that, you check the flow balance. It's 2 equal to 2, 2. 1 equal to 1. 1 plus 1 equal to 2. That is okay, right? That is the flow to the sink. The total flow will be 3 here. 1, 2, 3. Then you see that that's an optimum solution. Therefore, you see that at this one we can label the last signal, okay? The last node. Therefore, we stop. Therefore, solution. That's it. And therefore, in summary, first of all, forceful question is, first of all, find out feasible flow by, let's say that setting each arc flow to 0 will do, and then we start to label procedure and try to modify the flow until we cannot modify anymore. I determine K1 and K2. That's okay. It's quite simple. Now like this, actually this is example from here to here. The optimal flow is sync is 3. Okay. Now, unfortunately, I sent to you the solution already. But could you write this? Okay, let me explain this one also. It's better because normally now suppose that we have the network like this, and this number indicate the capacities. Okay, therefore our duty is determine the maximum flow from source to sink. Okay, at the beginning of feasible flow, you see that we set it 0, like this, right? Set it 0. And if you like, at the beginning, you will label the sink by 3. Okay, that's the first one. Then with this initially, we apply the reverse one. The reverse method, we try to find out K1 and K2 also. We determine the first step, we need to determine the reduce arc or increase arc first. Then we find out the K1 and K2. Then we do that. And the next step, we will label the zinc SO 1, 2, and 3. 2, 3, like this. Actually, this is quite short. You can, in this case, we try to label this one by increase this one is 2, increase this one 2, then this one is 2 also. Therefore, the total of this one will be adjusted 5. We increase is 5 because here 3, from 3 here we increase the maximum, the minimum increase K2 is 2. Therefore, all of this is here. Then from here we adjust again. That's label the zinc SO 2, 1, because here is 1 and zinc. Okay. Therefore, we increase 2 and 0 because we cannot go here. Therefore, you see that we cannot backward. Go backward is 0. It's still here. It's fine. Therefore, finally, you see that when we increase this one, we have to reduce this one too, to make sure that it's balanced. You see, that's it here. That is, you see that finally all of sync node to be labeled. The sync node to be labeled already. Therefore, this is optimum solution, and the total flow will be 8 in this case. The total flow 8 or 7.
Không có coi TikTok bậy bạ.
That's it. 7. Sorry. 2 and 5 is 7. That's the solution.
Không có tưởng ba mẹ không có nhà hả?
Okay. The algorithm is very simple, but this algorithm you see that it takes a lot of steps behind that. The first step we have to determine the increase arc and reduce arc. Then we have to find out K1 and K2 for each one. It takes a lot of calculation. Even it's very easy. Okay. You can in here due to the time limit. I just explain quickly for that one based on one by one increase. But in details, we have to perform like this, like before. The first step we have to increase, determine reduce, increase. Then we have to find out K1 and K2. Then adjust one like that. Okay. Any questions? Therefore, at the beginning, we think that normally we think that it's very complicated, but actually to solve it is not so difficult. Just in this method, the first step, we need to identify the increase arc and reduce arcs. Then based on that, we can adjust by the K1 and K2 or K. If it's only forward arc, like this, like this one, like these examples, this is a forward arc. The first one is forward arc. We always find out the minimum of in this one. That's the minimum of increase. You see, at the beginning is 0, you see. Therefore, we can increase, minimum increase of this one is 3. Therefore, we increase 3. Then after that, and in this one, we the increase arc, increase arc, increase arc, increase arc, and increase arc, right? And we have the reduce arc also. This one reduce arc. Therefore, in that case, we apply the second case that you see that we determine K1 first. K1 is 2. And K2, you see, so that's why here is 2. K1 and K2 is minimum of K2 is also 2. Therefore, the mean of K1 and K2 is 2. Therefore, you see that in this one we can for the increase arc we increase 2. You see 2, 2 also, and all of this 2, 2, right? Then behind that's one, and you can check back at home step by step for all of sequence here until we cannot adjust anymore. Then this solution will be optimal solution. If we do slowly step by step, the first one will be determine what arc to be the increase arc or reduce arc. This one is both reduce and decrease. For example, like this, I can write for you. In this case, reduce and increase also. Okay, because but in this case is only reduce, right? And in this case increase only. Okay, because it's zero flow. Then and from here to here, actually we apply the case one. We apply the case one because it's forward. And if you like, you can apply this one at the beginning is forward also. That's a forward arc. Okay, then after that we adjust based on case two. Because here after that the network include both reduce and increase arc already. Therefore, we have to determine K1 and K2. Okay, that's it. Take a break now for 15 minutes, then we come back to finish the second method. Okay. If you don't have any question, if you have any question, just feel free to ask me or we discuss later.
mắt đi. Ba Trung ơi con mắt đi. Em một xíu ra chạy. Ba Trung ơi, em bông đái, không mặc biển. Em bông đái rồi không mặc biển. Đái ra sàn rồi. Em bông ó ba. Bông đái ra sàn nhà. Bông đái á. Em bông đái, không mặc biển. Em đứng ở đó em vô không có chạy. Không có chạy. Không có chạy. Ba bông đái mà bông đi lăn tăn.
Đâu?
Nè.
Trời ơi bông ơi, đi vô đây nữa, nhanh lên. Bó tay luôn.
Con này con thấy á, bông cùng mắt bi á.
Cái gì? Bước vô đây đi. Sao không mặc điểm vô? Không mặc điểm thì đái phải nói chứ. Ủa cái chip bước ra mà.
Okay, come back, please. Now we continue with the second method. I don't know which is better, but two methods are simple. This method we call the free flow push algorithm. The idea of this method is quite different a little bit. This method based on the idea, in general idea, that the flow can run from the high position to the low position, a point. Okay, that is the general idea of this method. Okay. In details, you see that they say that this method they call the relaxation method. They perform local update repeatedly until global constraint is satisfied. It's similar to that we try to adjust the flow between 2 points. Each are small smaller and gradually until we cannot push it further. Okay, so that's why
Không có bước lên
this
giường
one
nha
we
Long.
call a push algorithm. Free flow, it means that we try to set up
Đưa cái chân này Long
the
vô.
condition before the
Bước vô đây Long vô đây.
product can flow.
Không có bước lên giường nghe chưa?
And you see that the idea, the fluid can flow from the higher point to the lower point. That's the main idea of that one. Therefore, at the beginning, the source node is the highest point because you see that everything flow from the highest levels, flow down to the lower levels. The sink and all the nodes are the lowest point. It means that the level of the sink and all the nodes in the network will be 0. And at the beginning, we will set its biggest levels for the source node and how big it is. I will show in the algorithm. Then the source send the maximum flow on each outgoing edges. The idea now, after high, they will send biggest flow to all of their local arc. The local arc is mean that the arc connect to it directly. The maximum volume. Send flow out to our neighbors is called push operation. It means that we push from the source node to the neighbor arcs with the maximum flow. The height of the source neighbor is then increased. You see that after receiving the product from the source, then the neighbor node will increase the height in order to continue to push. Okay, continue to push. Oh, sorry. Let me share then. I don't know why I cannot share now. Yeah. Can you see? Okay. The source send the maximum flow on each outgoing edge. Then after that, the neighbor nodes, okay, the height of neighbor nodes will increase.
Viết bài xong chưa?
Then the fluid can continue to flow out. Okay. You see that the idea is at the beginning the source will be rise up maximum, and it push maximum flow to the neighbor arch, to the neighbor nodes. Then the neighbor node after receiving is rise up. Then the fluid will continue to flow out again.
How are you?
The increasing height we call that relabel. It's similar what the way of for focusing method.
Okay.
Now,
what is your
a node is allowed temporarily to have more flow coming into it than flow outgoing. In this case, you see that because the flow grow gradually, therefore you see that the balance condition cannot be satisfied because the flow in always bigger than the flow out. Therefore, in this one, it's temporarily only, okay? And this amount we can, the different amount we call that is set flow at each node. But the S must respect the capacity condition. Of course, we can set the flow, but the flow inside of each arc cannot be bigger than the capacity of the arc. Okay? The source have arbitrary amount of each set flow. Okay? The flow of the set flow of the source node can be any random value, but in each node the set flow will be the difference of incoming flow and outgoing flow when the levels of the node is rise up. A node is said to be active if it has its set flow in it. It means that if the node have its set flow, it's not balanced. In that case, we call that node is active. We increase the height of the active node with relabel operation if H is the minimum height among neighbors that can accept flow. Then the height is relabeled by increase one by one. Okay, that is the way we update the active node. Okay, the active node will be relabeled. It means that will be rise up the height by the minimum high of the previous node to increase one. Okay. Then we push the exact flow tip node and can emit flow. It means that not exact the capacity can emit flow. It means that the arc still have capacity to receive. Third, make them active. Algorithm continue when we don't have any active node because when we don't have any active node, it means that the flow is balanced on every node. Okay. Now look on the example you will see. Now in this example, you see that at the beginning, we have sync node and terminate sync node, source node and sync node, and we have four node. Then here H is in the high. At each node we have the high. The source node we have only high. We don't have the exact values. Okay, we don't have exact values. But for every node, remaining node, the high at the beginning is zero. The exact value is zero. Also, we don't have exact value yet. Okay, and at the beginning, we have the value of capacity for each arc here. Capacity for each arc, and the current flow for each arc is zero. Okay, that's the beginning. And the notation high is the high of the node, and the exact flow E is noted is the first value of the capacity, and the second value is the flow. Now, the first step, we set the high of the sync node of the source node. The rule to set up of the high, the beginning high of the source node will be 6 because it's equal to the number of nodes in the network. In the network, we have 1, 2, 3, 4, 5, 6. Therefore, we set the beginning high of the source node is 6. Okay, that's the first step. Then the idea is we push as much as possible flow because the high of the neighbor node of the source node is 0. Therefore, it can flow out. Yeah, but the rule is we can push as much as possible the flow from the source node to the lower one. Okay, you see that we push 10 from here because the maximum amount we can push is 10. In that case, we can push 12, the maximum amount. Okay, therefore the exact flow of node E, you see that they receive 10. Therefore, they receive 10, but in this side it is 0. Therefore, the exact value is 10. In this side is 10. Therefore, in this side is 0 and 0. Therefore, exact value is 12. Right? Okay. Exact value of E is 12, and exact value of A is 10. It's not updated yet. Now update. Now we update that. It's 12 and H. Don't pay attention from H. Okay. So the next step, we can for the next one, you see that this one and this one in the next neighbor node. Therefore, we need to rise up this one. Okay, rise up this one by you see that here. We increase the height of the active node with the label operation. Okay, here we have 2 active nodes, right? Because the exact amount is bigger than 0. Okay, therefore this is active node, this is active node, and we choose, in this case we choose the minimum high among the neighbor that can accept flow. Okay, that is we increase 1 here. The high is the minimum high. In this case, among that one is 0 and 0. We increase 1. Then we label that one is the new one. Okay. Go back here. Then we push the exact flow to neighbor that are lower than the active node and can meet flow. Thus make them active. Okay. The main algorithm is this one. We increase the high of active node to be relabel operation. Relabel operation is what? Relabel operation is we rise up the high, okay? Increase the high, we call that relabel. Okay, in this one, we increase the high of this one. If you don't like, you can high up this one, but in this case, I choose C. Okay, I rise up high. Therefore, with this one, I push because this high is 1, this 0, therefore I can flow here. Okay, I push C and D. Okay, then I push 6. It set flow to 6. Okay, that's it. Okay, for the ED now will be 6. Okay, and similarly, after push 6, okay, I finish here. That is where I did not update here yet, right? E here is 6. Actually, because it takes a lot of time to redraw this, therefore I don't update it. It's 6 here. Okay, then that's it. Finish one step here. Then therefore, at this one, this will be active node, and this will be active node. But you see that here we have not finished this one yet, because here we still have the flow. Can admit that. You see that we continue the push the accept flow to the neighbor that are lower than active node and can admit flow. Here we just push one flow. We can push one flow. It can admit it. It push 6, right? We can push 6. Therefore, this one also still can admit flow. Therefore, we put 5 also. Where we put 5, therefore, you see that the accept flow value here will be fitted, right? E now will be fitted. And if you can redraw it, you can update that one, fitted. And you see that we will, because before we push it, we have to update rise it up, because to push it down is high. Then now we rise up. You see that here we push 5, we push 6 is 11, right? And this is active. Therefore, it's better. We push 1 along relabel C to 7 to be higher than this one, in order to push it back 1, in order to make it balance, right? To finish, because when we consider one active node, we try to finish it by the end. Then we'll move to another node. In this case, node C. Okay. Then after node C, we move to here. You see that that's 5 and 6 is balanced already, and the accept node is 0 already. Then now the active node, the next active node is A, because now is high is equal to 1, right? A and accept value is 5 because 15, because this is 10 and 5 here, that's 15. And this is the high is 0, therefore we push it 15. It can admit 15, that we push the total excess, right? Total excess values to this one is 15. Then actually the excess will be 15, okay? Then H here will be 5. Then this one in the past is 6, actually 6. Then after that, I will show you why it's 5 later. Then we finish this one already, because in this one is balanced already, 15 balanced. Then we move to the next node to be active. Actually, you can choose one or this one, it's up to you, no problem. But in this case, we will rise up S equal to 1. Then S equal to 1, we try to push as much as possible out. In this case, we push 3, okay? Therefore, except for this one is 3. And push 8 out of this. This will be 8. 8 received with 6 is how much? It's 14, right? SD 14. 14. Therefore, you see that we relabel. We rise up this one again. to 2. Then we push back 4 because here you see that with 3 and 8 only, that is totally 12. Therefore 11. Therefore we have to push back here 4 because in order to push back we have to rise up here to 2 because here is 1 only. Then push back 4. EI is 4. Okay, that's then we finish balance of this one. And you see that after pushback, this one, see that after pushback, this one is finished. The H set is 0, but this one is still active. We will consider this one later on. But now this is active. Therefore, you see that it's 14 because of receiving of this one is 8 and 6, 14. That's 14. Therefore, you see that we relabel this is S equal to 1, increases. Then we push maximum out. For this one is 17. 17 here. Push out. Then you will see that it's updated here. S is 17. 17, but you see that now this one is 14 only. Therefore, we have to push back. This one, the input is push back 14, but this 17. Therefore, we have to push back how much? Push back along. Oh no, that's B, not AB. Here, that's D. Where is D? Sorry. D is 17, right? We push this one is 17 fully. Therefore, this one will be. One is 7 only here. ET is 17. E of D is 17. Then this is push out is E of this one is 17. Then after that, here is not balanced. Therefore, we have to adjust this. This is 11. This is 15. Therefore, we push 4. Okay. 4 along A and B because this is 15, this is 11. Therefore, we push 4 here because the set here is 4. We write up here is 3 to be higher than that one is 4. Therefore, it's 15. Then this is all of this is non-active node already. Therefore, only this one is active node. Therefore, we need to push 4 along AB. Again, to relabel, that is EA4 here again. Then EA4, then with A5, we push again EB4. And this one is, you see that already, this is not balanced yet because it's 4. Okay, if we push back, move forward, back, and it's cannot solve. Therefore, it's go to here. That's it. 15 is finished. Therefore, we push 6 again. S rise up, B and push back again, because you know that it's somehow is repeating. It cannot get out of this one because the high level. We increase the reason we're repeating like this because the high of this one. It's not the biggest one. Okay, then go ahead. Then now is 7. That's the biggest one. It's equal to this one. We're repeating this one, this process in order to make this one bigger than this one in order to the flow this one. Okay, because you see each time we can increase S in 1 unit only. We cannot increase more. Therefore, we can push forward and backward in order to increase S. In this process, in order to make this bigger for adjusting this one later. Later on, we can push back 4 here in order to reduce this one, right? Then you see that 7 and 6. Therefore, we push back this one to increase of 10. We push back 4. Okay. Therefore, we put back here is 6. Okay. That's make this one balance right now 11. Then on this one also, we do the same way. repeatedly and until we don't have the excess flow between this node. And you see that S7 we flow 6 fully capacity. Then therefore you see that at this one is 14. Therefore we have to push back here until this one is 0. Then it's 14. You see that push back. Actually, this process do not show clearly here, but you will see that at the beginning is 14. That's the 14. Then we push here 14 only. 14, not 16. Sorry, correct for me this one. 14, not 17. Push 14. Push 14 here, therefore is 14, not 17. ED. No. ED is 17, yeah. ED is 17, correct? ED is 17. ED 14. ED now, after push, 14 here. 16 and 14 here. That is set here is 14. Then after we push it, this one 17, but this one is 0. This one 0, this one 17. Okay? And we stop here. And you see that it's balanced. Therefore, we don't consider back. Then we come back to consider this one to rise up in order to adjust this one. Because the reason as I told you that this one is not high enough to adjust this one. Therefore, we have to repeat backward and forward in order to rise up H in this side. And you see that that's a finish already. That's a balance already. Then we finish. This is balance already finished. Balance already finished. But this one is not balanced yet. Therefore, we backward and forward until it's adjusted here. And you don't surprise that. Why we move forward and backward until H here will increase. When H here increase, we can push back here is 4 in order to reduce it to 6 in order to make it balance. And that is the optimum solution. And you see that in order to here we don't have no active node yet left except the terminal node. Then we can stop. And if you want to find out the maximum flow, we have another concept we call the minimum cut. Minimum cut is the one include the arc can divide the network into 2 parts. And the flow in this arc sum up will be the flow of the network. That is 17. Okay, that's a 14, 3, that's 17. Or if you like, you can sum this up here, it's 17. That's the maximum flow on this one. Okay, do you need me to explain again for this one? Yes or no? Yes or no?
Hi teacher, yes. Can you just one more time?
Okay. One more time, okay. First of all, remember that you need to, you know the ESET flow, right? ESET flow first. The second one is active node. Active node is a node, not terminate node. Have the ESET flow, okay? Okay, active node is the node have the ESET flow. And the reliable is mean that we rise up the node. That's the reliable, okay, the high. The idea of this one is in order to make the flow, the high of short node, original node should be higher than the receiving node. Now, at the beginning, you see that only the short node have the highest one is equal to 6, equal to the total number of nodes. And remember that each iteration we can adjust only 1 unit of the high only. Okay, remember that's one. And the ESET at the beginning for all of remaining node is 0. Now at the beginning from short node, the high is 6. The high of neighbor node will be 0 and 0 here. Therefore, we need to push the flow out of short node with the volume that they can admit it. It means that it can admit capacity. In this case, we push is 10. We push is 12. Therefore, the excess values of this node will be 10 or 12. Okay, like this. Excess value of A will be 10, and excess value of 12 will be C will be 12. And we put it here is 10 and 10. Okay, here 10 and 12. Okay, that's the first thing. Then among this one, because this one have the excess node and this one have the excess one, therefore both of them will be active node. You can choose randomly which one is better. Normally we choose the bigger one to be the active node. Then when you choose this one is the active node, actually this one also is active node because the excess is different than 0. Then you relabel. This one is mean that you rise up in 1 unit. You rise up 1 unit, okay? You rise up 1 unit here, high. Then when this is high, therefore flow can flow from here to the lower one. Can flow from here to the lower one. Then from here, you can push 6 maximum. Okay, therefore the excess of this one is D will be 6. Okay. Okay, and we also push this one 5 here. The excess one of this one will be 5. Totally will be 15. Okay. Push. When we want to put, we rise it up because whenever we push it, we rise it 1 unit. Therefore, it's SI. Then 2. But you see that now it's 5 and 6. It's not balanced. And this is 12. This is 11 and 12. Therefore, in order to make it balanced and we finish this one, we need to rise up this one to be higher than this one to push back 1 unit to make it 11. Therefore, the graph now is 11 and this one is finished. And this one will not be the active node anymore. Okay? Because we push all of excess out. And you see that this is 15. Okay? This is 6. And now this one is active node because excess node the maximum one is 15. And therefore we rise up in 1. And we will push maximum amount of this one 15 to B. Therefore the excess of B will be 15. You see that here. Then B now you see that this is 0. Therefore this one not the active node yet, and this one will be the excess active node because this one is set is 15, the biggest one. Even though this one also active, but this is bigger. Therefore we choose this one is active node. Active node, therefore they will push maximum to the neighbor. Here the first one they push 3 to node D. Okay, they push 8 to node D. Okay, that is. Therefore the excess of this one after 8 it will be 14, right? 8 will be 14. Then you see that 8 and 6, 14 is okay. Therefore, temporarily, you leave it there. This is 3, 3 is okay. You leave it there. And actually, that's it. It said it's 3. But now, you see that you check back. This one is not balanced. You see that. Now, A is 10, 15. This is balanced, sorry. Balance this 15, this 15. Okay. But this one is x equal to 1. But the set here is 18, 8 and 3 or 11. 11, therefore, this one, the set of this one is 4. 15 out of 11 it will be 4. The remaining is 4. Therefore, you know that this is full capacity already. Therefore, we don't know. We don't have other way to adjust this. Therefore, we need to push it back here. Therefore, we have rise up B to push minus 4 back. Okay. Therefore, EA will be 4. Okay. EA will be 4. After push it back, EA will be 4, and this one will be 0. And this one, in order to push it back, this one rise up. Okay. Then, but you see that when you push back, this one will be 11. 11 and therefore you see that this one is not balanced. This 15 and 11 is not balanced. Therefore, you see that here. Then temporarily you accept this. Okay, leave it there. But now this is 14, this 14. Then this is active. Therefore, the last here the Z node is 4. The last Z node is 14 here. Therefore, this one will be the active node. This one is 14. Therefore, you push 14 here. Then this one will be 14 plus 3 will be 17. 17, you see that? 14 and finish. And you see that will be Z is 0. This is finish here. Then you see that in the whole network, only this one is 4. Therefore, this one to be the active node again. Okay? This one active node again, but this one is 3. Then you see that here is full capacity, this full capacity. Therefore, you don't have all the chance to adjust. Therefore, you have to push back here. Rise up here, 3 to push back here. Therefore, this one is 4. Okay? 4 is like the game. 4, then you see that it will be 15. 15, it will be 15 here. Then at this one, you see that here is 4, but this one is full already. I don't have any other chance. This one is active node again. Therefore, I have to rise up this one here, rise up higher than this one to push it back here. Therefore, it is 0 again. Then this one push back is 11. Okay, that's it 4 again. And we repeating that process in order to adjust this one, you see, to rise up until here. Until this one is bigger than this. Not yet. Forward and backward bigger than this one, then we push back here. Then you see that it's balanced until this balance. Therefore, it's 0. All of this one is 0. Therefore, our system is optimal. That's it. The most difficult point is the forward and backward because we are full capacity. Therefore, we have to rise up until it's higher, and then we push it back until this one. Okay. The procedure cost, you see that here. If this is in this work list of the excess node, okay, then if not, we relabel. Relabel is mean that rise up. Then if N can push flow to W and push flow, then we add up. Then if any node have the excess flow, we can add it. If not, we will stop. Okay. Therefore, go back home, study this one carefully, especially this step at the beginning of this one. After we finish this, everything is 0, right? After we finish this, everything is 0. 0 only, except this one and this one. But this one is full, therefore we cannot adjust. Therefore, there's only one way we push it back. That's the 4. Then, because this high is lower, then we cannot push it back here. Therefore, we move up and move up until we are higher than higher than this one. We can push it back, then we finish. That's it. Okay. You see that the neighbor, the idea of this one is graph, and the nodes with excess active node is not with excess flow. We call that neighbor active node and their neighbors. Then ordering is unordered. Parallel shoot at the beginning and drop down depend on the number of active nodes. Okay, that's it. Actually, the take time for this one is conversion to the optimum solution. And the high of the node direct flow to the sink. That is always the high direct from the source to the sink. Okay. Therefore, it affects flow of fluid. The reason why we have flow backward and forward because the high here is, you see that not higher. You see here it's not from the high from the source to the sink. It's not actually the high from this side should be higher than this side. Okay, that is some summary for this one. And you see that after global labeling, you will have the same way like this: move backward and forward, and yeah, that's it. Actually, the principle is similar. That every and a post label operation can build the high every node from the sink, and the high compute read first scan for residual graph. Okay. That is the clear examples. For actually the principle is the same, but you see that H, and finally we have not active node here, and it's also the reset node is 17, and here we write clearly about the forward and backward like this. Then we have this one. Okay, the main idea for this one is we try to adjust flow for each arc until it's balanced. That's the first one. And we always choose the active node with the current active node with the maximum of each flow. Maximum each flow. And we will try to make it to be pushed forward or pushed backward. It depends on the condition that we have or not. But when the forward arc is full capacity, we will stop. We don't continue. Therefore, you see that line is balanced like this. Better to stop it, and we will push backward here to make it balanced. So that's why we rise up. We always do like this. Okay. That's it for today. Any questions? Actually, this algorithm somehow is difficult a little bit for this one compared to Fock-Fulkerson. Fock-Fulkerson is more difficult in terms of choosing in terms of calculation. You see that we have many steps. First of all, determine the reduce and increase arc. Then we will adjust, select the forward arc first. Then in the case of reduce, and we have to determine K1 and K2. But it's easier. It's more step to calculate, but it's easier than reflow. Reflow somehow that we be practice more in order to make sure that we understand that okay, with this one the active node with the maximum set flow will be the active node, and we will push forward. But in the case of push forward, if fully capacity is already like this, then we have to think about the push backward in order to make the node flow to be balanced at that node. And this one is active node, then this one will be active node. You see that. Then between this one, you see that here the question, the main point for this one is this one. The forward already full capacity, the backward also full capacity. Therefore, we prioritize that we push backward. Okay, we don't push forward, right? Because that's the priorities for this one. And we push backward until you see that the high here we adjust it to the sink. That's okay. Any questions? Okay, if we don't, you don't have any question, I will stop here and see you next week for the homework. Okay, the homework I already sent to you, and we have around two lecture labs for the minimum cost flows and multi commodities. Actually, you see that we know how to formulate the problem in the correct form, we can solve it easily. Then by that way, you can determine the correct plan for distribution system easy. And next week we will study the minimum cost flows. We actually shortest part as you study in OR1 is kind of minimum cost flow, but it's not general. In some cases, we need a more general problems than minimum cost flows is popular in real life. Okay, thank you. See if you don't